wait 5 more minutes that will start. Okay, so hi guys, welcome to the week 4 lectures of fundamentals of MIMO. Okay, so hi guys, welcome to fundamentals of MIMO tutorial. I am Rubina Afin, PMRF fellow from IIT Hyderabad. I think there are lots of noise coming, so I'll just fix the issue. Okay, so we will start. So what we have done in previous week, we were discussing about received signal correlation. So what we had seen was that received signal correlation we wrote as expectation of RT into RT plus delta T. So this we saw has come in terms of phi HI delta T cos of omega Ct minus phi HQ delta T into sine of omega Ct. So as we have already seen, RT equals to real part of HT e to the power j 2 pi Ct, right? So from here we can write the correlation of received signal as real part of correlation of channel into e to the power j 2 pi Ct. So from here we can write channel correlation as phi HIJ delta T plus phi of HIJ delta T. So in the lectures you must have seen that phi of HIHQ delta T when computed was equal to 0. And phi of HIHI delta T is equal to omega p by 2 J0 2 pi of max delta T. Here J0 is the first order Bessel function. So from here we know the channel correlation. So phi HH delta T we can write as phi HI delta T, which is equals to omega p by 2 J0 2 pi of max delta T. So this is all about receiver correlation. If we plot it, this axis is FT delta T. Since this is Bessel function, this will decay after some time. So from here we can see the receiver correlation as well as the channel correlation. One important thing that I would like to discuss here, see, whatever we considered here, we had considered isotropic scattering. So that means that in the expression we have taken p theta as uniform, right, which is equals to 1 upon 2 pi. From this diagram we can see that the correlation is like at FD delta to f 0.4, this correlation is almost 0. Here it is the 0 axis. So this is one important point, that from here we can see how much the antenna spacing is. We will see more about it in a special channel. Maybe we should discuss. So this diagram I have taken from the book. So you can see the uh, correlation is 0 at around FD tau equal to 0.4. If we consider special channel, we suppose that mobile is moving. So now suppose this is your receiver antenna. This receiver antenna travels for a distance delta x in time delta t with the speed v. What we can say is delta x equal to v times delta t, right? Now we know that V by C of Fc is Fm. So V we can write as Fm by Fc into C. Now if we substitute it, expression for delta x becomes Fm by Fc into C into delta T, which can be written as Fm delta T upon Fc into C. So what we are trying to do is that Fm delta C we are trying to express in form of delta x. We will see why. So Fm delta T we can write as delta x times Fc upon C. And C we know that C is equals to Fc into lambda. So Fm delta T, this we can write as delta x upon lambda. This is an important result that we will use. So for isotropic scattering, what we have written was phi HI delta T correlation of the channel. This is omega p by 2 j naught 2 pi Fm delta T, right? So this we can express in terms of delta x. Phi HI in terms of delta x can be written as 2 pi Fm delta T we can write as delta x by lambda. So this is for the HT correlation. Alpha we can write as modulus of HT, and correlation for this is given as mu alpha alpha into delta x. This is given by this expression which is given in the lectures. You can refer to the lectures for this. So this is 5 by 16 omega p j naught square 2 pi by lambda into delta x. So basically what I want to say is, suppose here you see FD delta T, this is delta T for our discussions. So FD delta T is 0.4 for correlation equal to 0. So from here we can write as delta x by lambda is 0.4 approximately. So delta x is approximately 0.4 lambda, or if we relax it more we can say lambda by 2. This means that for uncorrelated signals, what we have to do is that we have to space the antennas at around lambda by 2 distance. Okay. So if antennas are spaced at lambda by 2 distance, every antenna should have an independent fading path. They will not be correlated. So this is one important concept that I want to discuss. Also, one important note, that results will change if p theta is different. Right? So there we considered isotropic scattering. That means that the signals are coming from all directions. with equal intensity. That is why p theta we had taken as 1 upon 2 pi. Now suppose if we are saying that LOS component are existing. So what I mean to say is that signals are coming from all directions, but there is one signal with higher power. So suppose it has k is to 1 ratio. So in this case, p theta will change as 1 upon k plus p hat theta. This p hat theta is uniform that we had considered. So now all the 1 upon k minus all the uniform components will consist of this 1 upon k minus 1 upon k plus 10 fraction of power, and the other LOS component that will have k upon k plus 1 term. Here theta 0 is the angle of arrival of specular component. So this component comes from scattering, and this component comes from specular component line of sight. So we have the autocorrelation expression. We have found the correlation between the received signals. Now suppose we have to find the power spectral density. So since only in phase component is present, so we will find the power spectral density of this. So whole calculation is given in the lectures. I will just write the results. So this is equal to omega p by 2 pi fm into 1 upon square root of 1 upon f by fm whole square. So this term is valid when it is valid when magnitude of f upon fm is less than equal to 1, so that the denominator is positive. So this f will always be less than equal to fm. If we plot this with respect to f, so we can see that there is very high power at minus fm and fm, when f equal to minus fm and f equal to plus fm, and when f is 0, the value is 1. So this value is 1, and this is very high power. So this is the power spectral density. This is known as Doppler's spectrum or GX spectrum. Okay, so why Doppler spectrum? Because obviously it is due to the mobility effect. And again, I will want to say that p theta is assumed as 1 upon 2 pi r. That means isotropic scattering. If we have one LOS component, so then the PSD will vary as there will be one specular component here. So you must have seen that type of question in, I guess, assignment 3. So we will move on. So we will be discussing about frequency selective fading. Okay. One big assumption that we made during flat fading channel is that there is one transmitter and there is one receiver, and when signals are going from transmitter to receiver, getting reflected. So we assume that all the reflection is happening on one ellipse only. That means whatever path the signal is taking from transmitter to receiver, it is encountering the same delay. Right. So this happened in flat fading channel. Now for frequency selective fading, I'll maybe draw a better diagram. Maybe I'll explain it later. See, the signal will be reflected from various points between the transmitter to the receiver, but these need not be on the same ellipse. They can be anywhere. Like suppose they can come from here, they can go from here, or they can go from there, there, like that. So we discussed all this in the week 1 tutorial. So what we are doing is that we will assume that all the reflections are happening on any ellipse only. Like for the flat fading channel, we had taken that all the reflections are from this one ellipse, which has the delay tau. Now we will assume that there are multiple paths, but then all of them will lie on one ellipse. So initially this was tau, now this is tau 1, this is tau 2. Likewise, multiple paths will be there. Suppose there is one another ellipse with the delay of tau 3. Obviously it will be in both directions, and then signal will be reflected from this one. Then the other one is tau 4, like that. So for flat fading, we have seen that the channel is varying. In terms of time, the channel is varying, but in terms of delay also, it will be varying. For flat fading, there was only one delay, but now there will be multiple delays, right? So we will take this delay axis. Now suppose this is tau 1. And this is the time axis. So the signal is varying along with the time axis, right? Suppose any kind of variation is there. So now what we will assume is that likewise, like we have assumed for tau 1, for tau 2, similar signal will be there, which is varying with time axis, right? For tau 3 again, the signal will be varying with time axis. So in flat fading, we have determined channel correlation from here. Now we will be determining, we can determine channel correlation for each delay. Like phi hh tau 1 will be the parameter for this one, phi hh tau 2 will be for this one, phi hh tau 3 will be for this one. So basically this is the channel at different delays. I'll explain it better. Let's change the axis, take the delay here and the time here, like we have done in the previous one. So suppose this is tau 1, this is tau 2, this is tau 3. Okay, so this would be the channel. The channel will be varying with respect to time. What it means is that at each delay there is a sum of multipath, right? In multipaths are then summed up, which is a time dependent variable. So for each tau, there will be a HT existing, which has its own PDF, and then which we can um, calculate the correlation, everything. But the gist is that for different delays, these ellipses that I have drawn, this signifies the delays, and this inner one is for the tau 1 delay, suppose. So for tau 1 delays, as you can see the lines in blue, these are multiple reflections that are happening at the delay tau 1. Then again at the delay tau 2, different reflections are happening. So this is a time varying channel. So this is h of t at tau 1. This is h of t at tau 2, and likewise. So what we have done previously is that we studied all the channel nature that was on only one delay axis, like what is the type of channel, relay fading, Rician fading, Nakagami, whatever we have done, that was on a single delay axis. So like these suppose these are the channels for different delays. This can be relay, this can be Rician, this can be Nakagami, anything can be there. So the correlation and PDF, two parameters from which will be describing the signals, these need not to be same for all distributions. So this can be, suppose this can be relay, this can be Rician, likewise. So one important thing that we can conclude from here is that at the delay axis, some sort of profiling is happening, right? So we will see this in power delay profile. Now we will see how this is frequency selective fading is happening. So as we have seen that for each delay, multiple paths are getting added. So if you see my tutorial 2, I think. So what we had, the expression there was ht tau is equal to summation n equal to 1 to n cn e to the power minus j phi n t delta of tau minus tau n. So for each delay, for each tau, this channel coefficient is a sum of n reflections, where we have n amplitude variations and n phase variations. Phi n t we had expressed there as 2 pi fc plus ftn of tau 1 minus ftn of t. So this was our original expression. Now as we are taking different delays, we can write it as phi n theta as 2 pi fc plus this Doppler frequency, we can write it as f max cos theta and theta into tau n for the tau minus again f max is theta n theta into t. The path inside the inside any one delay, there is a phase associated. Sorry for the disruption. So there is a phase associated with all n paths. Now again we can write h theta is equals to c of n theta for the first delay path into e to the power minus j phi n t comma tau 1. So this is like coefficient for first delay path into delta of tau minus tau 1. Then again for the second path we have this n theta 2 to the power minus j phi n t comma tau 2 delta of tau minus tau 2. So likewise it will be added. So we are taking different n theta 1, n theta 2, cn theta 1, cn theta 2, like because for each delay there will be n number of paths and that n number of paths is not same, right? So suppose like for tau 1 delay we have suppose sum of 20 reflections, and for tau 2 delay we have suppose 15 reflections coming up. So this is not same. So that is why for each delay we are taking different coefficients. Now if we do Fourier transform of this expression, so we have again Fourier transform like we have done in the single path, like single delay system. We have taken Fourier transform with respect to tau, not with respect to t. So here also we will take with respect of tau. So h in frequency domain will be a function of t, but it is Fourier transform with respect to delay. So this is so after computing the Fourier transform, the expression is maybe I can write it shortly as h of t comma tau 1 into e to the power minus j 2 pi k by nf into first path plus again h of t comma tau 2 into e to the power j 2 pi k by nf into 2 plus and so on. This is a very important concept. You should go to the lecture and maybe practice it out on pen and paper. So from here we can see that how there are different paths, but then they are resolvable. So likewise this Fourier transform. Okay, this is in the time limit. We can say that this is Fourier transform of h of t comma tau 1 plus Fourier transform of h of t comma tau 2, and so on. It will go on till Fourier transform of h of t comma tau max. So this we can write as so even if there are different delays, all the different delays are resolvable. Like we can literally resolve them. So now we have the H expression in frequency domain. So what is happening is, suppose if there is only one delay path, so that time we saw that the channel is flat feeding. Like, now if we are taking two delays, so what is happening is if there are large number of paths, then some frequency will be attenuated, but then some will be some will be more attenuated, some will be less attenuated. So suppose we have taken more delay, like suppose two tap channel we have taken. So this is there. If we increase the number of taps, then more variations will be there. If we increase more variations will be there, like this. So there are some selective frequencies which are less attenuated, and then some selective frequencies which are more attenuated. That is why this is called as frequency selectivity. Okay, so as we will be increasing more number of paths, then some frequency will be allowed and some will be more attenuated. So here we see this angle, this axis is frequency and this is gain. What we are seeing is correlation in frequency, how much the signal is correlated in frequency. So as the number of taps are increasing, as the number of paths are increasing, then there is less and less correlation. You see the variation for hello. So the variation for two tap channel is less. There is more correlation. But as the number of taps are increasing, as the number of paths are increasing, then the correlation is less and less. So now when we observed spread in time, that time we saw coherence timing. Now we will define coherence bandwidth. So now our signal is coherent in frequency domain. So this coherence bandwidth is now given by is proportional as 1 upon tau RMS. Where tau RMS is the RMS delay spread. This we will discuss. This is coherence bandwidth. So we have two coherence bandwidths defined. This is BC 0.5 is 1 upon 5 tau RMS. This is called as 50% coherence bandwidth. And then we have BC 0.9. This is 1 upon 50 tau RMS. This is 90% coherence. So as from the name, this is when the signal coherence is 50%, and then this is when the signal is 90% correlated. Okay, so this is one concept. Now what happens because of multipath fading? So these and all are resolvable delay. We assume that the first path is near because the delay is less. So propagation path from the first path will be smaller. If we take this as delay axis and this as time axis. This is the gain. So basically, hello, I think I'm having some disturbance in my network. Okay, so uh, at every delay, suppose this is tau 1, this is tau 2, tau 3, and so on. So at every delay, n number of multipaths are there which are getting added, and which gives rise to this h of t. So this is h of t at the delay tau 1. This is h of t at the delay tau 2. Then this is at the delay tau 3, and so on. And this is the time axis. If we see this as t1, then this will be nothing but h of t1 comma tau 1, h of t1 comma tau 2, likewise. And then at some other time t2, there will be a signal, and then it will have multiple echoes at the different delays, right? So what is happening is that at any time one signal is generated. This is one impulse response, and these are basically the echoes of this impulse response at different delay times. So we can say that the impulse is getting spread in the time domain. Okay, so basically h of t1 and tau 1 and h of t2 and tau 1, these two are the same signal impulse response which are studied at two different time intervals t1 and t2. So what I mean to say is that uh, this is tau 1, so this is again tau 1 axis, and then there is one impulse response h of t2 comma tau 1. So what we are saying is that if t2 minus tau 1 is much lesser than the coherence timing, then h of t1 comma tau n is approximately equal to h of t2 comma tau 1. That means that both of these will be in the same magnitude, and then since tau 1 is same, then it will be same phase as well. So this is slow fading in time, right? Because with the time the channel is not changing. h of tau 1 at any delay tau n is equal to h of tau n at any delay tau 2. So we can say that it is a slow fading. Now we see this power delay profile again. So what I'm doing is here three things we will have to study. Like suppose this is tau max. So this will be the maximum delay spread. Okay. Now we will see average delay spread and RMS delay spread. So what is delay spread? Delay spread is the difference between time of arrival of earliest multipath component and the last multipath component, right? So I will write it down. That it is the difference between time of arrival of earliest multipath component and last multipath component. So average delay, or we can say as mean delay, this is given as tau bar equal to integration 0 to infinity. If discrete power delay profile is there, we can use summation, but general formula is this. So tau times of expectation h tau square d tau divided by average power. Okay, so this is the mean delay. Now we have RMS delay. So RMS delay, tau RMS is given as, we can write it as integration 0 to infinity this we can write as tau bar square minus tau m square. Average delay we can define as tau m, mean delay. So tau bar square is given as integration 0 to infinity tau square expectation h tau square d tau divided by 0 to infinity expectation of h tau square d tau. So before we move forward, we have this tau bar square and tau m square. So tau RMS we can find as square root of tau bar square minus tau m square. So before we move forward, we will see some questions. Okay, I think it got cropped a bit. So this signal power at 5 microsecond is 0 dB. Now it is asking maximum delay spread and average delay spread. So what would be the maximum delay spread? As we have seen from the previous power delay profile, the maximum delay, the time at which the difference of time at which the first component is arriving and the time at which the last component is arriving, that is known as the maximum delay spread. So maximum delay spread tau max would be equal to 5 microsecond, right? Because at 0 we are getting, and then at 5 microsecond also we are getting. So maximum delay spread would be 5 microsecond. Now average delay spread, mean delay spread, we can write as so this would be we have to convert this power into linear scale, right? So minus 10 dB would be 10 to the power minus 1. This would be 10 to the power minus 0.5, and this would be 10 to the power 0. So mean delay spread would be 5 times of for 5 microsecond. The power received is 0 dB. So this would be 5 times of 10 to the power 0. Okay. After that, the next one is at 3 microsecond. The power received is minus 10 dB. So 3 into 10 to the power of minus 1. And then at 2 microsecond, this is received as 10 to the power minus 0.5. This would be divided by, and this is 0 times of 10 to the power minus 1. So that I haven't written. This would be divided by 10 to the power 0 plus 10 to the power minus 0.5 plus 10 to the power minus 1 again plus 10 to the power minus 1, because we are receiving 4 signals. So this is received at tau equal to 0. That is why we haven't taken it in the numerator. So solve this and you will be able to get the average delay as 3.9 microsecond. So the answer would be A. Now you see in the previous problem, what would be the RMS delay spread? So for this, mean delay spread is 3.9 microsecond, that we know. We will compute tau bar square. This would be equal to tau 1 square p tau 1 plus 4 are there. So tau 2 square p tau 2 plus tau 3 square p tau 3. P tau 1, tau 2, tau 3 are the power at the different delays. Then it is tau 4 square into p tau 4 divided by p tau 1 plus p tau 2 plus p tau 3 plus p tau 4. So first one is 0, second one would be 4, 9 and then 25. When you calculate it, it would be 0 into 10 to the power minus 1 plus 4 into 10 to the power minus 0.5 plus 9 into 10 to the power minus 1 plus 25 into 10 to the power 0 divided by all the powers. That is 1 plus 0.1 plus this is 0.1 plus 10 to the power minus 0.5 would be 0.316. Then again it is 0.1 and then this is 10 to the power 0 is 1. So this would come as 17.918 microsecond. We put it in the formula for tau RMS. This is equal to tau bar square minus tau mean square. This would be equal to 17.918 minus 3.9 whole square. When you calculate it, it will come as 1.6 microsecond. Okay. So this answer would be D. Now you see this question where h of tau 1 comma tau and h of tau 2 comma tau are given. So as we discussed previously, these are like two impulse responses seen at different times. So these are the two impulse responses of a channel at two different time instants, tau 1 and tau 2. So it says that tau 1 minus tau 2 is very less than coherent time. Okay, so we have discussed right that if t1 minus t2, if the time difference is very less than coherence time, then we have h of t1 comma tau is approximately equal to h of t2 comma tau. That means that the signals are same in magnitude and phase angle. Because phase angle also because these are calculated at the same delay. So it would be almost same in magnitude and phase angle. Right? So RMS delay spread we saw is given by tau RMS, and then mean average delay we have seen as tau m. So this tau RMS is important. This tau RMS gives the channel characteristic. Like it tells us if an impulse is sent, then how much the channel envelope will spread. Right? Like what we are doing here is if this is our delay axis. So initially we only had one delay and the channel was here. Now we have the echoes of the channel component, right? So there we can see as there is a delay there is a spread in delay. So tau RMS gives like how much for any impulse response sent. I'll write it down for any impulse sent. How much is the spread of the envelope? Okay. And then tau max, that is the maximum delay. This goes as 5 to 10 times of tau RMS. This 5 to 10 depends upon different propagation environment. So there is that is why this is very wide range 5 to 10 times of tau RMS. So based on this we will see this question. Here the RMS delay spread of a wireless channel that is experiencing frequency selective fading. So frequency selective fading, that means that it has different multipaths, right? So RMS delay spread is given as tau RMS. This tau RMS is given as 1 microsecond. Now it is asking maximum access delay. So tau max will range in between 5 to 10 times of tau RMS. That means it will range between 5 microsecond to 10 microsecond. You see the options. So all the other options are very less. So the correct answer should be C. That is 5 microsecond. It and it says that it is likely to be. It says likely to be because the range is very varying. This will depend upon the propagation environment. Okay, now angle spread we will be discussing. So till now we have seen the wireless communication channel. Uh, I will be adding one page. So this is a wireless channel. So what we have seen till now is that it is either time selective or it is frequency selective. And now one more thing we are adding. This is space selective. Whatever assumptions that we are making right now, this will be continued further in MIMO and all. So this is a very important thing. Time selective channels we have seen as two types: slow fading and fast fading, right? Then frequency selective channels we have seen of two types. This is flat fading and frequency selective fading. Now space selective channels are of two types. There is rich scattering and poor scattering. This slow fading and fast fading, this how we knew. We knew it from Doppler spread. Right. For frequency selectivity, we discussed delay spread that we were discussing till now. And for rich and poor scattering, we will be discussing angle spread. I'll write it down everything and then I'll carry on to angle spread. For Doppler spread, uh, we defined coherence time that is inversely proportional to Doppler spread. Here we defined coherence bandwidth that is inversely proportional to delay spread. Okay. So here we are defining coherence distance that is inversely proportional to angle spread. Okay, so for coherence time, what is coherence time? Coherence time is the separation of time for which the signal is correlated. Coherence bandwidth is the separation of frequency for which the signal is correlated. Likewise, coherence distance would be separation of distance for which the signal component are correlated. Okay. So these are very relative. Now you can relate between them. Like if we have Doppler spread, if we have coherence time. So if coherence time is there, time. So the channel is time selective. Time selective means it can be slow fading or fast fading. If we are given coherence bandwidth, then the channel is either flat fading or frequency selective fading. Or if we are given coherence distance, then either it is from rich scattering or poor scattering. So here we will discuss it once. See what happens in rich scattering is that there will be scattering from everywhere, like signal is coming from everywhere. For poor scattering, the signal is narrowed like this. So there is a narrower angle in between. So when there are lots of reflection, then we consider the rich scattering channel. And if there are lots of reflection, then obviously the signal will not be correlated. Okay. So in this case, for rich scattering, so for this rich scattering, coherence distance will be low. So always remember, when there are lots of reflection, then it will not be much correlated. That is why the coherence distance is low, and consequently the angle spread is more. For poor scattering, what happens is that less scattering is happening. So the signal is coming at a narrower angle. So in this case, angle spread will be less. And since it is poor scattering, so the signals will be more correlated. So here the coherence distance will be more. Okay. Now you see this question. Coherence distance is inversely proportional to. So this is very obvious. It is inversely proportional to angle spread. Okay. For delay spread, this is coherence bandwidth is inversely proportional to delay spread. For this Doppler spread, we will have coherence time, which is inversely proportional to Doppler spread. And here it is coherence distance. Okay, now we will move on to the next question. So this is asking about wide sense stationary uncorrelated scattering channel. So this is like combination of two processes. One is wide sense stationary, and then other one is correlated scattering. Okay. So now we will see it one by one. See, uh, any channel is there. So if the channel is wide sense stationary, that means that the autocorrelation of the channel will be depending upon delta tau. Okay. So here autocorrelation will depend upon delta tau. For uncorrelated scattering, the autocorrelation is dependent upon delta f. So you can refer this concept in the lecture. So the important thing is that this impulse response of the channel at two different delays, tau 1 and tau 2, it says are uncorrelated. No, it is definitely correlated. So at different Doppler frequency are uncorrelated. No, because the uncorrelated scattering means that it will depend upon delta f, and wide sense stationary means that it will depend upon the delay. But then impulse response at two different time instants are not considered. So this is not true for the wide sense stationary uncorrelated scattering. Okay, so you can look for this concept in the class in the lecture 4 tutorials, week 4 tutorials, and just let me know if there is any doubt. But then wide sense stationary process and then uncorrelated process, uncorrelated scattering channels are defined like that. And then one is the homogeneous channel that you can see in the lectures. Maybe I should just let you know that for homogeneous channel, the autocorrelation is dependent upon delta D. So now we will move on to the multi-user channel. Some space is there. So here some assumptions we are taking. One assumption is that always we will take any channel as flat fading channel. Okay. So now moving on from this point, all the channels will be flat fading channels. Okay. So first thing is this single input and multiple output combination. So this consists of one transmitter and then multiple receivers. Suppose MR number of receivers are there. So this will count for MR different channels, right? In this case, we can write the channels as now we are assuming as flat fading channels. I'm writing it here. So all the channels will be h of t comma tau, that is for the single delay, and this we will write it as h of t. Okay. So for single input multiple output, the channel will be h of t is h1t, h2t, and so on up till hmrt transpose. That means it is a column vector of h1t to hmrt. For these Seinberg channels, and for every communication channel, we have y equal to hx plus n. This we discussed in our first tutorial also. for SIMO you have uh, multiple outputs, right? So there are multiple receivers. So we have y1, y2 up till ymrt at the receiver. Okay, and at the transmitter we have a single x. Okay, so this is a mr cross 1 vector. This is multiplied by h, which is also mr cross 1 vector. This will be multiplied by the single input x, and then as there are mr different receivers, so you know that the noise gets added at the receiver because of receiver imperfections. So if there are mr receivers, so noise will also be mr cross 1 vector, right? So this is all about single input multiple output signal. So for here we can write it as yt is h1t xt plus h2t xt and so on, plus all the noise cumulative as nt. So all the received signals are copies of the same signals. Okay, so these are the different copies of the same signals. As we discussed previously also, that this is used to this is important because maybe if some link is broken, then in that case we will get a proper output even if some link is broken. So this is its significance. Then we have multiple input single output. Here we have multiple antennas at the transmitter, and the receiver only has single antenna. Okay, so we can say that empty transmitters are there. So this is H1T, H2T. Any general HT can be written as HJT and so on. So now you can see that there is only one receiver. So again you see y equal to hx plus n is there. So x is empty cross 1 vector, right? And y is single. So it is all a function of time x1t, x2t, like that. And since there is only one receiver, so only one noise will be added. Okay, so here you can see that this will be a row vector. Okay. So this is multiple input single output system. Now we will have MIMO communication system. So MIMO will be having multiple transmitters and multiple receivers. So these are the empty transmitters and there are MR receivers. Now there would be channel between each transmitter and each receiver. Okay, this would be H11. So the nomenclature I had also taught in my first lecture, week 1, week 2 lectures. So this will be receiver and then transmitter. Like this is for the second receiver from first transmitter. So this will be H21. Likewise, suppose if this one is the link, then you can write it as H2 comma empty. This link would be H of MR comma 2, like that. So now at the receiver we will have, since we have MR receivers, we will have MR cross 1 as the received signal. Again we are again using the same things, y equal to hx plus n. X we have as empty cross 1, and then since there are MR receivers, so MR noises will be there. So noise is MR cross 1. So now the channel would be MR cross MT. Right. This would be H11 T2, H1 MTT, likewise HMR1 T2, HMR MTT. So since in this case matrices are involved, so that is why we will write it as y is equals to HS plus M. So at any receiver I, suppose YIT is summation j equal to 1 to MT Hij of t into Sj of t. You can see here. Suppose this y1t is there. So this y1t would be x will take till x t of t. So this y1t would be h11t till hmtt. So for any receiver, the number of transmitter will go from 1 to m, and then it will be h times of s. Okay, a few more questions first we will see. After that, we will go to the concepts again. So here RMS delay spread is given as 1.5 microsecond. Okay, so tau RMS is given as 1.5 microsecond. Now it is asking 50% and 90% coherence bandwidth. So we have seen previously as coherence bandwidth, 50% coherence bandwidth is 1 upon 5 times of tau RMS. So this will be equal to 1 upon 7.5 into 10 to the power minus 6. This, if you calculate, this will come as 133 kilohertz. And then you have to calculate 90% of coherence bandwidth. So this is 1 upon 52 or 50 tau RMS. So this will be 1/10 of the 50% coherence bandwidth. So this is 13.3 kilohertz. So the answer would be D. Now this question you see, what is the minimum physical separation required between adjacent antenna given a rich scattering environment? So now the rich scattering environment, why is it mentioned? We are told that the correlation formula that we derived that existed when p theta is 1 upon 2 pi. That means that we are using isotropic antenna. So isotropic antenna, that means that signals will come from all directions, right? This is what is rich scattering environment. So we had defined earlier that for the rich scattering environment, how much would be the physical separation? It should be lambda by 2, where the correlation becomes 0. Okay. Now this is a channel covariance matrix. So the channel covariance matrix R, this R is defined as expectation of wake of H into wake of H Hermitian. We will see what wake of H means. Suppose H is Consider MIMO. So suppose H is MR cross MT. So wake of H will convert this MR cross MT matrix into a vector of MR MT cross one size. Okay. Uh, One simple example we can see. Suppose A is a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 9, 8. So what would be the vec A? What would be the size of vec A? So this is a 3 cross 3 matrix. The vec A size would be 9 cross 1, and it will take the first column 1, 4, 7, and then stack it over the second column 2, 5, 9, and then stack it over the third column 3, 6, 8. So this is basically what this vec of any matrix is. Okay. So we are seeing the R matrix. Sorry about that. So this is the covariance matrix R. So vec of H is of the size MRMT cross 1, right? So this would be multiplied by permission of this one, that is 1 cross MRMT. So this will result in a square matrix. Okay. This R is called this R is said as positive semi-definite matrix. So for any positive semi-distinct matrix, for any positive semi-definite matrix, all the eigenvalues are real, distinct, and positive. Uh, we can say it as non-negative. That means greater than equal to 0. It can be equal to 0 also. So here it is given as properties of the positive semi-definite matrix. So the eigenvalues will be real as well as distinct as well as non-negative. So the answer should be all of the above. Now see this question. Suppose we have a matrix A of the order of m cross n. Then the order of decay would be, as discussed, it would convert it into a vector of n cross 1 size. Like, suppose n cross n, then like A would be n cross 1. So the answer would be C. Now this question is about zero mean circularly symmetric complex Gaussian MIMO channel. So any classic IID channel, what we are assuming in MIMO is that delay spread is negligible and the channel can be modeled as circularly symmetric complex Gaussian. Circularly zero mean circularly symmetric complex Gaussian. So suppose we have z equals to x plus JY. So what does complex Gaussian means? That X and Y both are Gaussian and the mean is 0. So this means that is why it is called zero mean. Now this term is there, circularly symmetric. So the property of circularly symmetric random variable is expectation of e to the power j5 times of z should be equal to e to the power j5 into expectation of z. So now see this question. We have z as the element of channel matrix of zero mean complex circularly symmetric complex Gaussian. So the expectation of z e to the power j5, this would be e to the power j5 into expectation of z. But then since z is zero mean complex Gaussian, so the expectation would be 0. Then the expectation of z e to the power j5 would be 0. So it is always 0 without any conditions. Okay. Now moving on to this question. See, we have a model y equal to hx plus n. So we have this yt as mr cross 1, and we have this h as mr cross mt, and then we have x as mt cross 1, and then this n is mr cross 1. Sorry, this is mr. So this is yt, this is h, this is xt, this is nt. For single input, single output, mr is 1 and mt is 1. That means that y is a scalar because this will be 1 cross 1, h is a scalar, x is a scalar, as well as n is a scalar. Now for single input multi output, mt is 1 and mr is, no, this is single input multi output. So a single input multi output. Okay. So mr is mr. So here we will have yt as column vector, then h also as a column vector, xt is a scalar as we had discussed previously, and then since there are multiple outputs, multiple receivers, so nt is also column vector. Then we move to MISO. Here we have multiple input, we will write mt as mt and mr as 1. So here we can see if mr is 1, put it as 1, then output will be scalar, y will be scalar, and h will be 1 cross nt, that means it is row vector, and then x is column vector and n is also a scalar, and this can be justified because we have single output, so single noise source will be there. And then MIMO, this already is the equation for MIMO. Okay, so it is asking about single input multiple output channel, and for single output multiple input mt is 1, so the channel matrix would be a column vector. The answer would be B. Okay, this we have already seen, this is 5 microsecond. So I'll give some more questions. So one important concept, and then we will discuss one more question. So this is about narrowband antenna array. Now suppose we have two different antennas that are separated by a distance d. The wavefront is coming perpendicular to the antenna array. So this is the wavefront. And it makes an angle of theta. So the spacing between the two antennas is d, and then this Tz is the time difference at which the signal will uh, go from first antenna to the second antenna. So Tz is the time difference between the signal to reach the first and the second antenna, right? So we have the narrowband antenna assumption. This says that if B is the bandwidth of signal, then for narrowband B should be much less than 1 upon Tz. Okay. Now suppose one question we will see. So here Tz is given as 5 nanosecond, and then it is asking that on which bandwidth the signal can, the narrowband antenna assumption can be taken. So suppose first option is 100 megahertz, second one is 200 megahertz, third one is 10 megahertz, and the fourth one is 1 gigahertz. So we have to tell when the arrow can be said as narrowband. So Tz we have Tz we have 5 nanosecond. So 1 upon 1 upon Tz we can calculate as 1 upon 5 into 10 to the power minus 9. That is 200 megahertz. So for narrowband assumption, we know that B should be much lesser than 1 upon Tz. We see the options. So in these options, option C is much less than 1 upon Tz. So here the most likely answer would be option C. One question more is there. So we have a mobile station that is moving at the speed of 500 km per hour. So this is the suppose mobile station. This is moving at the speed of 500 km per hour. Okay, so it is using a 2.4 gigahertz carrier frequency. FC is given as 2.4 gigahertz. So to accomplish channel equalization, it measures the channel coefficient at regular intervals. So what should be the maximum measurement interval? Now since V is given, first we will convert the kilometer per hour to meter per second. So 500 kilometer per hour will come at around 138.8 meter per second. So here the Doppler frequency would be V by C times of FC, that is 138.8 divided by 2.4 into 10 to the power 9, and it should be 2.4 into 10 to the power 9 divided by 3 into 10 to the power 8. Let's do some calculations. So this FD will come as 1110.4. So from here we can calculate the maximum measurement interval. We will discuss this question again in the next class. So I think to summarize, we have discussed wireless channels till now. We have taken the time selective, frequency selective, and today we have discussed the space selective channels. In case of time selective, we have slow fading and fast fading channels. In case of frequency selectivity, we have flat fading and frequency selective fading. And in case of space selective, we have the rich and poor scattering. Okay, so in case of time selectivity, we will see the coherence time. In case of frequency selectivity, we will see the coherence bandwidth, and in case of space selectivity, we will see uh, the coherence distance. Usually, one concept I will discuss here. If multi-part delay is less than Ts upon 10, and if multi-part delay is greater than Ts upon 10. So in this case, the delay would be much less than the symbol duration, and here the channel would be flat fading. In this case, the channel is frequency selective. Since this is flat fading, this is not time resolvable. But the frequency selective channels are time resolvable. So since it is not time resolvable, this means that the channel components are not distinguishable at different times. In this case, the components are distinguishable. Okay. In case of flat fading channel, there is no ISI. But in case of multipath, delay is more, then the intersample interference will be there. As we have discussed this in week 2 classes, that if delay would be there, then this would lead to the intersymbol interference, because different symbols will be coming at different times. Okay. Also, one same channel, this same channel can be flat fading for one user and can be frequency selective for one user. It all depends upon the symbol duration that is reaching them. So we can see this from the coherence time. If coherence time is greater than symbol duration, then it is flat, otherwise it is not. Okay, so I think this much is sufficient for today. Any question left will be discussed in the next week tutorial class, and we will be uploading this recording as well as this PPT. You can watch, and then in case of any doubt or discussions, you can post on the discussion forum or maybe mail me separately as well. So I'll be happy to help. And this is sufficient for today. We'll meet again in the tutorial 4, where this is the week 4 tutorial. We will meet again in fifth week tutorial, and then we will be discussing all of MIMO. So that's all for today. Thank you.